Okay, here we go. Okay, everybody see my everybody see the slides?
Yes.
Everybody see
Yes.
that?
Yes, doctor.
Okay, so last time you were on slide number 20, okay, or 19. Okay, slide number 20 here. We have two mechanisms. Okay, this mechanism by which holes and electrons move through a silicon crystal. Okay, and they are called diffusion and drift, or drift and diffusion. Okay, so a drift, okay, that will produce current drift, and the current drift occurs when an electric field is applied across a piece of silicon. Okay, therefore, free electrons and holes are accelerated by the electric field and acquire a velocity component called drift velocity. Okay, and this drift velocity, or v drift, is equal to mu p times E, where mu p is the mobility constant of holes, in this case of holes. Okay, and E is the electric field strength. Okay, this is, we are talking about right now. We are talking about what? A piece of p-type material. Okay, but this one here also applies to the n-type. Okay, so for the n-type will be mu n E. Okay, guys. All right. Okay, now the drift, if you have a piece of silicon like this, which is the p-type, because we are talking about p-type, okay, and you apply external voltage to it, and you will develop electric field E. And therefore, the current IP, okay, is equal to cross-sectional area, which is A, multiplied by Q, okay, which is the charge of the holes, in this case, times the P, which is the concentration of holes, okay, multiplied by the V drift, okay, or the drift velocity, okay, of holes, okay. All right. Okay, guys. So as I said here, an electric field E established in a bar of silicon causes the hole to drift in the direction of the E, which is the electric field, okay, and the free electrons to drift in the opposite direction. Okay, both holes and electrons drift currents are in the direction of E. Okay. All right. Okay. All right. Any questions? Okay. Diffusion, the second one is diffusion. Okay, particle diffuse from a region of higher concentration to regions of lower concentration, okay, due to random thermal motion. Okay, so if you have a piece of silicon and you drop, okay, say you drop high impurity concentration on one end, okay, and you wait for a while, this whatever you drop at one end, it will diffuse slowly, okay, to the other end. Okay, it will drift slowly to the other end. So, over here to the left will be higher concentration, and over here will be lower concentration. Okay, and this is the direction of the drift. Okay. So if we look at the bar of silicon, okay, you can see the holes concentration profile shown on B here, okay, and you can see it, created on this is x-axis, which is this is the distance here, okay? And you can see, you know, at 0 here, which is at this end, the concentration is high, while the concentration over here at the other end is low, okay? Current density, okay, due to the drifts or, due to the drift or diffusion, sorry, not the drift, but diffusion.
Doctor,
Yes.
there's one guy messaging me on WhatsApp. He's not in the Teams. He's asking if you can add him.
Now?
Yes.
Okay.
His ID number is 2019-0975.
What is it? This is it, Jasim?
Yes.
I thought I added him before. No, I didn't add him.
لا أنا جاسم بس إنه في طالب ثاني. There's another guy.
What's his name? What is that?
نزار
What's his name?
عادل.
Well, ask him. Nizar Adil, where is he? Ask him to send me a message on chat. Okay. All right. Ask him to send me a message. Okay. Where are we? We are here. Okay. So the diffusion. Okay. The diffusion. As you can see, this is from higher concentration to the lower concentration, and the particle will diffuse slowly. Okay. Same thing here. You know, you can see the whole concentration profile. Okay. And the current density in this case for the current density due to the holes is given by Jp is equal to minus Q dp over dx, where Gb is the current density and Q is the magnitude of electric charge. Of course, it is what 1.6 times 10 to the power minus 19 coulomb. And dp is called diffusion constant of holes, okay? And dn is diffusion constant of electrons, okay? As you can see, this is Jn due to the electrons, and this is the Jp due to the holes, okay? And they move opposite to each other, and that's why, you know, this is negative and this is positive, okay? Okay, guys? Okay. Take care of, there you go. Okay, Nazar. Copy. Okay, Nazar, you are in. Okay. Okay, guys. Any questions so far? Very good. Okay. Okay, any questions? All right. The relationship between diffusivity and the mobility, we call this, you know, they call it Einstein relationship, okay, is that dn over mu n is equal to dp over mu p, okay? And this relationship is equal to Vt, okay? Vt. What is Vt? Vt is the thermal voltage, and it is equal to 25.9 millivolt, okay? Our book equates Vt to equal to 25 millivolt, okay? But you know, almost all the other books, okay, they equate it to equal to 26 millivolt. However, when I give you problem or when I give you quiz or anything, I will mention what is VT equal to. Okay, so whatever you do not forget, VT. Okay, V capital T, that means thermal voltage. Okay, very important, guys. If you forget it, then you will solve problem incorrect. All right. Before we leave this slide, go ahead and try to solve 1.8, page 47 in our book. Okay, summary here. Okay, this is how we created N type, how we created P type. Okay, and we mentioned about pure silicon is an insulator. Okay, and type temperatures and conducted weekly and stuff. Okay, now we created N type and P type. Now what we're going to do with them? Okay, now what we're going to do with them is that we're going to put N type and P type. We're going to join them together. Okay, join together, and we'll see what we're going to produce. Okay. So what we're going to do is this is the N type, okay, and this is the P type. We join them together, okay, and what we make, the product we made, we call this PN junction diode. So we created a PN junction diode, and what happened is that almost all the silicon chips. Okay, and your computers, on your cell phone, and your whatever, okay, is made of something like this junction. This is a PN junction, except the transistor has more, okay, and thermostat and everything is a little bit more junction. Okay. I think this is old. A silicon chip may have 10 to the power 9 PN junction today. Actually, maybe it's 10 to the 20 or 10 to the 30 PN junction. Okay, so when we put them together like this, okay, we put a metal over here, okay, and a metal over here. Okay, so why do we do that? It's because we want to solid contact with the N-type silicon and solid contact with the P-type silicon over here. And then we put terminal here. We call this terminal on the N-type side, we call it cathode. And we put the terminal here on the P side, and we call this anode. Okay, so remember, this is the anode on the P-type side and the cathode on the N-type side. Okay. Okay, now, since we brought them together in contact, how we're going to analyze what's going on at the middle here, okay, at the middle, okay? This is the junction here, okay? What's going on in the middle? And that's on slide number, the next slide, okay? The next slide over here, slide number 27. Okay, so when we zoom in at the middle here, we look at the atoms, okay, atoms, and we'll see this is the middle here, this is the junction, and we'll see this is the silicons atoms, okay, and this one here, the red, is the phosphorus atom, that's the pentavalent, okay, what we call it a donor atom, and over here on the P side we have boron atom, which is the acceptor atom. Okay, trivalent atom, okay? And if we look carefully, we'll see that the electrons, you see there are electrons here, okay, which form the majority carriers and the N-types. They are moving across the boundary to the other side, to the P side, and neutralize the hole. So the electron and the holes will be canceled out. Okay, or neutralized. And the process will keep doing like this, okay, until we set up an electric field. And the electric field will say, will say to the migration of electrons and holes, it will say, stop, no more, okay, migration, okay, no more migration. And then what will happen is, this is what will happen, okay? What will happen here is a region here, okay, is where the holes and electrons in this region are depleted, okay, are depleted. No more holes, no more electrons, all depleted, okay? And because, you know, we don't have holes and electrons in this region, we call this region depletion region. What do you call it? Call it depletion region. So, you know, when I ask you about what is depletion region, or somebody asks you what is depletion region, depletion region is a region, okay, between the N-type and the B-type, where the holes and electrons are completely depleted. And also all that's left is the positive and negative ions. See, these are the positive ions. Okay, and this one here on the other side is negative ions. Okay, and this one here is the electric field. Okay, the electric field that stops the process of migration of the electrons to and holes. Okay, so think about it, you know, like this. This is the positive, this is the negative. This is, you know, what some small battery, or what they call it, electrostatic field here. Okay, I got this from the internet, guys. Okay, because, you know, it's nice and clearly shown, you know, the depletion region and the electrons here and holes over here. Okay, all right. Okay, now if we look at the schematic diagram of the p-n junction diode, we'll see this is what N-type, and this is the P-type, and this is the cathode over here, okay, and this is the anode over here, okay. Okay, so the net acceptor concentration, we call this Na. So N, capital N, capital A, we call it net acceptor concentration. And over here, okay, we'll see the net donor concentration in D. Okay, and this one here, you know, this is the cross-sectional area, of course. Okay, now we don't want to do schematic all the time, you know, when we deal with a circuit. So we have to come up with a circuit symbol. Okay, what is the circuit symbol? Is here. This is the circuit symbol for the p-n junction diode, or in short, diode. Okay, and it is indicated by, this is the arrow over here. Okay, the arrow indicates the direction of the current ID. Okay, so this is ID over here. Okay, the current will never go the opposite way. So it always goes from the anode to the cathode. Never goes from the cathode to the anode. Okay, and to make sure that you guys understand that, okay, the manufacturer put what? A bar here, this bar. Okay, so that's, you know, when the current coming here, it will say stop. You cannot go the opposite way. Okay, so whatever you do, when I give you questions, don't assume that the current will go like this, from the cathode to the anode. If you do that, you'll get 0. Everybody got that? Okay. Across the diode, there will be a voltage called VD, okay, when we connect it to a power supply, of course, right? So this is the anode, this is the cathode. Okay, now physically, okay, when we want to manufacture the diode, okay, we start with N-type silicon, okay, N-type silicon. And we call this, you know, substrate. What do you call it? We call it substrate. Okay, and then we deposit P-type, as you can see here, okay, P-type. So I have N-type and P-type, so I created a diode here. Okay, and then, of course, you know, we grow silicon dioxide over here, silicon dioxide over here, and then the reason we did this is to isolate the other circuit, also other circuit from here, okay? And we put a metal, like that, connected to the p-type, and we call this anode. Okay, and at the bottom we put metal here, and we call this cathode. Okay, so the current will pass through here. Okay, the diode, think about the diode as one-way valve. Okay, guys, one-way valve or one-way street. You cannot, if you if you have a car, you cannot go and drive on the opposite direction of the road. Okay, if you do that, you'll get fined big time. Okay, maybe 50 dinars, 100 dinars. Okay, don't do that. All right, in this class, you will not be fined 20 dinars. Okay, you will get zero. Okay, that's your fine. Everybody get that? Okay, very good. Any questions? All right. Okay, now what we're going to do, okay, we're going to look at the diode. Okay, when the diodes have no external voltage, means no bias. Okay, we don't apply bias to it, to the diode. And then we're going to do what? We're going to do forward bias. Okay, that means the diode is on. Okay, that means forward bias. The diode is on. Okay, just like a switch. You switch the switch on. Okay, forward bias. And then we'll look at the reverse bias. Or we can look at the reverse bias first and then forward bias first. Okay. Okay. All right. As I said before, I just explained this, how, okay, when the two PN junction, when the P and then N-type connected together, of course, holds the fuse from the P side to the N side, okay, and so on. We just explained that, okay, and we created, the depletion region here. Okay, where the carrier or the majority carriers are depleted, and all left as the donor ion and acceptor ion at the in the middle here. Okay. Okay. Now, if I don't have any bias across it, or if I don't have any voltage across it, or if I don't apply any voltage across it, that means the VD will be 0. There is no current flowing, okay, across it. Okay, all I'm seeing is what? The depletion region. If I look at the N-type side, I will see the donor ions positive. If I look at the P-type side, I will see acceptor ions negative. Okay, so the profile of that, I can draw it like this. Okay, this is the middle here exactly. Over here, I will see the charge positive. Okay, from here to here, positive. Okay, and over here will be negative. Okay, so this is the charge density. Okay. All right, so that's how, the charge distribution. Okay, and over here, everything will be quiescent neutral. Everything is neutral, okay? Okay, guys, any questions? Okay, the same thing here. I didn't apply any voltage, no bias still, VD equal to 0. Okay, across the diode. The current I I will be equal to 0 because I didn't have any voltage across it. Okay, and this is the depletion region stuff. Okay. Okay. When we look at the diode in more detail, okay. Why did I put this? I put this is because when you go to the upper classes, okay, especially when you want to be, say, electronic engineer, okay, and you want to study in more detail, what's going on, across the diode. Okay, and in this case, what we're going to do is we're going to look at the band diagram. We call it a band diagram. What is the band diagram? Is over here. This is called band diagram. You see this? Okay, this is the p-type side. Okay, and the depletion region is like this, bent. Okay, and this one here is the p side, is the n-type. Okay, you see these are electrons, and you see over here these are holes. Okay, right now they can't cross. Why? It's because of this bend. Okay, this bend, they cannot cross, and that's why they call it band diagram. They cannot cross. Why is that? It's because we created here a junction built-in voltage, which is called VO. What do you call it? VO, junction, okay, built-in voltage, VO. Okay, so in order for these, okay, for the current to flow, okay, which is formed by the electrons and the holes, the band diagram has to be straightened up. Okay, it has to be straight, it has to be exactly straight. And how are we going to do that? We have to put a voltage to overcome this VO. Okay, we have to put a voltage to overcome this. When we overcome this voltage, then the band diagram will be straight, and therefore, the electrons and the hole will cross, and therefore, which means that the diode will be on. Okay. Now, if you want to calculate V out is given by this formula here. Okay. VO, sorry, which is the built-in voltage. VO is equal to VT. What is VT equal to? 25.9. Okay, this is the thermal voltage. Okay, natural logarithm ln Na, which is this is what acceptor ion. Nd, this is the donor ion. Okay, divided by Ni squared. This is the total of the silicon atoms. Okay, this is the silicon atom. So this is how you calculate V out. Okay. However, I usually give you the value of V out. Okay. Any questions? Okay. Okay. Now this is the definition here. What is the depletion region? Okay. As we said before, the depletion region is a region between the p-type and the n-type, where the carriers are depleted, and all is left is the negative and positive ions. Okay, this is a clear definition of depletion region. Okay, so wherever you go, this is it. When somebody asks you about depletion region. Okay. Okay. Now let's do reverse bias. Okay, let's do reverse bias where VD is less than 0. Okay. All right. Now to reverse bias the diode, okay, you put negative, you connect that negative terminal of a battery to the anode, okay, and positive terminal of the battery to the cathode. Everybody got that? Okay. Now what happened here is if we do that, the positive terminal will attract the electrons, and the electrons will move away from the middle here. Okay, will move away toward the positive, and the same thing, for the holes. Okay, holes are positive, will move away to the negative terminal. And what exactly we did in this case? We made the depletion wider. We made it wider. So the resistance of the depletion region increased dramatically. Okay, it will increase to maybe almost infinity. Okay, which means your diode is completely open circuit. Okay, when you are reverse biasing the diode, the diode is almost infinity, or open circuit, almost. I said almost, okay? Okay, now if we look carefully, you will see that there is a current here. There is a current here, okay? And this current here, why? Is because of the minority carriers. What is the minority carriers in the N-type? It's holes. What are the minority carriers in the P-types? Electrons. Okay, so there are small currents, very small currents in the microamp and sometimes in the nanoamp or picoamp. And we usually ignore this current because it's too small. Okay, got it? All right. Everybody get that? Okay, so that's how we do it. Any questions? Okay. So if we're going to look at the ID versus VD, okay, we will see this is the reverse current, which is the IS. When this is the current when the diode is reversed. This is actually a rough current. Actually, it is about microamp. Okay, but we'll see it later. We'll see its value later. Okay. Okay, guys. So as you can see from here, okay, this is the original depletion region. Okay, they call it barrier sometimes. Okay, but when we connect the negative terminal to the anode and the positive terminal to the cathode, we reverse bias the diode. The depletion region widen. Okay, and you can see that is widened here. Okay, that means its resistance will increase dramatically. Okay, guys. Okay, now what about forward bias? Okay, VD greater than 0. Okay, external voltage applied across the PN junction and the same polarity as the PN, okay, material. Okay, so as you can see, this is the anode here, positive, and this is the cathode, negative, as you can see here. So if we connect the positive terminal to the anode and negative terminal to the cathode, okay, and what will happen is that the negative, okay, which are negative carriers, the majority carriers, which are the electrons and the N types, and the holes and the P types, they're going to cross each other. They're going to push the force the depletion region, okay, and then usually they just destroy the depletion region, okay, and because the depletion region destroyed, you will get a current flow, okay, the current flow, and we call this current ID. What you call it? ID. Okay, so ID is equal to what? Is equal to I due to the majority minus I due to the minority. Okay, ID. Okay, which means that this one here, the book said narrow, but usually it's becoming like 0. What does that mean? It means that when you forward bias the diode will be on. Okay, just like a piece of, it will become like a piece of wire. Okay, got it? That's a piece of wire. So that's why we converted the semiconductor material, okay, which is in this case silicon, from just we depend on the we used to depend on the temperature to make it on or off. Okay, now because we modify the characteristic of the silicon, we created N-type and P-type and put them together. Now we can do the same thing. We can make the silicon now, which is the diode, as on, okay, which is a piece of conductor, or off as a piece of insulator. Got it? There you go. Any questions? Okay. When we connected the voltage, external voltage across the diode, most of the voltage across the diode will be dropped across the, most of the voltage of the external voltage will be dropped across the diode, okay? Be dropped across the diode. So, you know, in summary, if VD greater than 0, okay, the potential barrier to carrier diffusion is reduced by the applied voltage. Okay, if the VD is 0, which is the reverse bias, the potential barrier to carrier diffusion is increased by the applied voltage. Okay, what does that mean? It means, you know, when the supply voltage is sufficient enough, okay, and forward bias, the depletion region will be gone, okay, and you will get current flow. That's forward bias. If the applied voltage, external applied voltage, and is causing this one here, causing the diode to be reversed, then the depletion region will be widened, causing the diode to be switched off. Okay. All right. Now, for forward bias, we look at the profile of or the characteristic curve, okay, which is ID versus VD, okay, and you can see the graph here. It will go 0, 0.1, 0.2, 0.3, 0.4, 0.5, until it reach about around 0.7, and then all of a sudden it goes, okay, on, completely on, and the current here will be a milliamp. The current will be a milliamp, huge. Okay, so this is a forward bias. Notice that, you guys notice that at this time here, when the applied voltage, okay, is 0.1 volt, the diode is still off or reverse bias. 0.2 volts still reverse bias, 0.3 volts still, and so on until you reach around 0.6. What will conduct will be on. Why is that? Why is that, guys? Why is that? Why didn't we say when you apply a voltage here, any voltage, the diode will be on? Okay, it's because of the voltage across the depletion region, which is, remember, you know, the built-in voltage V out. Okay, so V out for the silicon, which is the V0, where is it? Did we mention that? We did. We did mention that, right? Okay, where is it? Somewhere here. We didn't, I think we missed it. Okay. I think we did mention it. There you go, see it? This V out, see it? Which is the built-in voltage. You have to overcome here so that the band diagram would be straight, so that this one here, the electrons and hole will move, and that's what makes the diode to conduct. Okay, got it, guys? That's why. Okay, that's what is it? There. Okay. So for the silicon, the VO, which is the built-in voltage, is 0.7 volt. So you have to overcome that. You have to put a battery, okay, big enough, okay, to overcome the 0.7 volt. You know, if you put, say, 1 volt, the diode will be on, of course, right? If you put 5 volt, will be on. But if you put a battery that is 0.3 volt, the diode will be off, okay? Because, you know, you didn't put sufficient voltage across it to overcome the built-in voltage, okay? Or sometimes we call it the threshold voltage, the one that you apply to it. Okay. Okay. Now this is on slide number 41. This is analogy, okay, of the diode. Okay, now over here you can see it's a water valve. Okay, water valve. Okay, and the water valve here has a diaphragm. This is the diaphragm, and the diaphragm is pivoted here. It can move this side or that side. Okay, now if you put the water, apply water from here. This is the anode. Okay, then the diaphragm will move away, and the water will flow like this. Okay, and that's that's an example of forward bias. Okay, forward bias. Okay, because this is the anode, this is the cathode. Okay, now if you try to put the water on the opposite direction, like here shown in red, the diaphragm will block the water, and there will be no water flow. And this is the example of reverse bias. Okay, so this is the reverse bias, this is the forward bias. Okay, and this is the symbol here. This is the cathode, and this is the anode here. Okay, sorry, anode, and this is the cathode. Okay, anode, cathode. Okay, now on top here, on top, this is the commercial diode. Okay, what does that mean? It means when you want to buy, say, a diode from a store, okay, IG store in Al-Hassam, you go to the Al-Hassam store and say, you know what, I want a diode, okay, normal diode. I said, okay, well, I'll give you diode, pay, 2 dinars or 1 dinar, something like that, and they will give you something like this, okay, something like this. And you take it home and you say, wait a minute, where is the anode, where is the cathode? Okay, well, the cathode has a band here, usually painted in silver here, okay, a band, silver. And this one here will indicate cathode, while the other one indicate the anode. Everybody get that? Okay, easy, easy. Any questions? Any questions? Okay, now we talk so much. Okay, I talked so much about the diode and forward bias and reverse bias. Okay, now let's see. Let's see a video. Okay, just a clip. Okay, there you go. Does it work? Doesn't work. No, it will work in a minute. There you go. Okay, you see this is the depletion region here. Okay, this is reverse bias. See the band diagram over here. Okay, this is the reverse bias. This is the what is it? This is electrons and this is the holes. Okay, look at this. Okay, now the band straighten up. Okay, now this is forward bias. See the depletion region? Okay, it's dissolved. Okay, now the depletion region is on. Okay, and the majority carriers are trapped. Okay, and over here is almost open circuit. Okay, got it, guys? There you go. Okay, look at this. Okay, so the depletion region is gone. The depletion region is gone now. Okay, now it is on, and you will have a current flow. Okay, the current flow like. Okay, this is from Lucerf University, something like that. Okay, any questions? All right. Now what we're going to do is we're going to calculate. Is there any question before we move? Okay, what we're going to do, we're going to calculate the width of the depletion region. Okay, and it is given by this QXP, okay, multiplied by the cross-sectional area, multiplied by the acceptor ion, okay, is equal to Q multiplied by N, okay, Xn multiplied by cross-section area N donor, okay. So the Q went out with the Q, and then the area is the same, okay, and also left is Xn over Xp is equal to Na over Nd. And that's mentioned in page number 56 in your book. Okay. Okay. Now the width of the depletion region, okay, W, okay, width, W, this is called depth, okay, is equal to Xn plus Xp. Where is that? Where is that? Well, there it is. Did I do it? I think I did. Okay. Maybe I didn't. I'm sure I did, but sometimes it's hard to see it. Okay, there. Okay, on slide number 57. So this one here, XP. See, from here to here, this is XP. From here to here, this is XN. Okay, so W depth is equal to XP plus XN. Got it, guys? Okay, very good. All right. So XP plus X plus XN is equal to root 2 epsilon Q multiplied by 1 over Na plus 1 over Nd multiplied by VO, which is the built-in voltage. Okay, where the epsilon here called the electric permittivity of the silicon. That is about what 1.04 times 10 to the power minus 12. Okay, and usually the depth is in the range of 0.1 to 1 micron, micrometer. Okay, now before, in the old days, we used to calculate the charge, okay, charge store on either side of the depletion region. Okay, this is also on this page also. And this is equal to the cross-sectional area multiplied by the root square of 2 epsilon Q multiplied by Na Nd over Na plus Nd times the built-in voltage. Okay. Okay, so why am I giving you this? Is this one here, I'm giving you these formulas, is because when you go later on and you want to continue your study on upper classes at other universities abroad, they will give you these. Don't say I didn't show you, I'm showing you now. Okay, guys, when you go to say Cambridge University or Purdue, okay, or Portland State or something like that, okay, you will see people are dealing with this. Okay, all right. Okay. Now we mentioned the 3 operating conditions of the diode. Okay, as you can see from the IV characteristic of the diode, and on over here, the origin here indicate that there is no bias. The origin here, okay, this is no bias. Okay, to the right is when the diode is forward bias. Okay, when you put positive at the anode and negative at the cathode, so the diode will be forward bias, and you will get something like this. Okay. Okay. Now the dashed graph here is produced by some equation 1.4. Okay, in the book. Okay. Notice the scale here. The scale, okay, is in milliamp. Okay. Over here to the left is when the diode is the reverse bias. That means it's almost open circuit. And there's a small current here, small current, okay, called IS, and it is around 0.1 microamp. Okay, very small, 0.1 microamp, or we can call it what? We call it 100 nanoamp. Okay, we can call it 100 nanoamp, very small. So we usually ignore that. Okay, we usually ignore it. Okay, guys, any questions? Okay. Slide number 47, sorry, 40, slide number 45, okay. I said here, you know, this is summary here. Said the point at which the diode changes from no bias condition to forward bias condition occurs when the electrons and holes are giving sufficient energy to cross the p-n junction. We have seen that, right? Okay. This energy comes from the external voltage applied across the diode. Okay. The forward bias voltage VT, which is this one here, is called this VT. This is not capital VT. This is not V capital. This is V small letter T. This is the threshold voltage. Okay, threshold voltage. This is the voltage at which the diode is just conducting. Okay, that's we call threshold voltage. Okay, so the threshold voltage for the germanium, okay, for the germanium is what? For the germanium diode is 0.3 volt. Okay, and for the silicon diode is 0.7 volt. Okay, and for the gallium arsenide is 1.2 volt. Okay, guys. So whatever you do, don't forget these voltages for germanium, okay, silicon diode, okay, and the gallium arsenide, 1.2 volt. Okay, guys. Okay, so you know to make the gallium arsenide to forward bias, the threshold voltage has to be greater than 1.2 volt. So that the gallium arsenide diode will be conducting, or will be forward bias, or will be on. So to make the gallium arsenide diode on, you have to put a voltage greater than 1.2 volt. Okay, or you know, around 1.2 volt. For the silicon, as we have seen from the graph, we have to overcome the 0.7 volt. We have to put at least 0.7 volt or greater. For the germanium, however, germanium diode, we have to put what? 0.3 volt or greater. Okay? Okay. Any questions? Very good. Okay, now we come to resistance levels. Okay, some semiconductors react differently to DC and AC current. Okay, there are three types of resistance. One called DC resistance, or sometimes we call it static resistance. Okay, and the other one called AC, or dynamic resistance, and the other one is average resistance, AC. Okay, so if we look at the DC resistance, okay, how are we going to calculate it? You know, we have this is the graph, the characteristic of the forward bias, okay, graph, and we just pick 2 points, okay, and we use Ohm's law. RD, which is the static resistance, is equal to VD over ID. Okay, easy. If you look at the dynamic resistance and forward bias region, RD, okay, is equal to 26 millivolt. What is this, guys? Anybody? What is this? 26 millivolt. Anybody? This is the threshold voltage, VT, okay, V capital T. Sorry, this is the thermal voltage, VT, V capital T. This is not threshold. This is the thermal voltage, okay, which is around 25.6 millivolt. But you know, if we round it around, you know, to the round it around, we can call it 26 millivolt. Okay, so this RD is equal to V capital T, threshold voltage, divided by ID, okay, plus RB. Okay, RB. where RB is, this is constant value is between 0.1 to 2 ohms, okay? When we are in reverse bias region, RD, okay, is equal to infinity. And therefore, you know, your diode will be off when you are in reverse bias, okay? Almost open, just like open circuit, okay? All right. If you want to calculate the average AC resistance, okay, our average, we look at the forward bias graph, and we take 2 points, okay, for the current and for the VD, and we use Ohm's law, delta VD over delta ID, and that will give us, you know, the our average, okay, volts, okay. Depletion or junction capacitance, okay, junction capacitance over here, okay, we call it CJ, junction capacitance. Okay, so the depletion region has a capacitance. Why? Is because, you know, it has on the N type, we call that, you know, one plate. On the P type is one plate, and in between those two plates, you have the depletion region. So actually, you created a capacitor, okay, kind of, right? We can calculate, you know, the capacitance when the junction or when the diode is in reverse is like this. This is the CJO, which is the initial, okay, which is a zero reverse bias, divided by 1 plus VR, and this is the reverse bias voltage, divided by the barrier or built-in voltage, okay, time to what M, which is what they call it, you know, gradient coefficient, which is a constant ranging from 1/3 to 1/2. Okay, all right. Diffusion capacitance, which is when the junction is forward bias, is given by CD, which is the diffusion capacitance, is equal to tau divided by VT. This is the thermal voltage multiplied by ID. Okay, where the tau is the transient time of the junction, and VT the thermal voltage, which is 25 or 26 millivolt. Okay, guys. All right. On slide number 52, okay, I put it there. Why? Because it's very important when you go to the upper classes. Okay, and you're going to deal with high frequency. Okay, high frequency operation, especially when you are dealing with Pentium or, you know, P5 or P3 or very high frequency circuit. Okay, you need speed. Okay, now the diode has a capacitance. Okay, and the capacitance, you know, it's not desirable. Okay, when you want to operate the diode as high speed circuit. Okay, why? This is why. Okay, because of this, what we call it, reverse recovery time, or TRR, which is the time required for a diode to stop conducting once it is switched from forward bias to reverse bias. So ideally, you know what we need like this. This is ideally, this is forward bias here. And we want to, when we switch it off, it goes like that. So it will be off. So what will happen, you know, in reality, in real life, this is our forward bias. Now we're going to switch it off. When we switch it off, guess what? It will not switch off immediately. It will take its time to go like this, and then it will go like that. So after that, over here, okay, it will be off. So, so what happens is that the reverse recovery time, TRR, is equal to TS, which is called storage time, okay, plus TT, okay, which is the transient time. Okay, this is the transient time. Okay, and this time could be, I mean, maybe, it's in microsecond, okay, something like that, microsecond. But, microsecond, when it comes to high-speed circuits such as Pentium P7, is maybe 600 million years. Okay, so what slows down your computer is stuff like this. Okay, this is what slows down your high-speed circuit. Okay, so if you are not careful and you want to design high-speed circuit and you put a diode like this, your circuit will be very slow. And you will say, why? It's because maybe because you didn't take this class or you didn't understand this. Okay, got it? Everybody got that? Okay, all right. Okay, now slide number 53. This is the end. Okay, I put a definition: what is valence, what is covalent bond, band gap energy, intrinsic, donor, okay, and so on. So with this, we finish this chapter. Okay, right now this chapter is done. Okay, and this one here is the foundation, okay, of what's coming later on. Okay, the foundation of all the chapters. Okay, this is the foundation of electronics. Everybody get that? Okay. Any questions so far? All right. No questions? Okay. Any questions, guys? Okay. If you don't have any questions.
Would you
Yes.
upload these slides, Doctor?
Yeah. This slide will be. Hang on. This slide will be over here. Okay, will be over here. See it? This is from last time. The slide. Okay, so it's all the slide will be on Teams. Okay, guys, got it? Okay. Any other questions? How you guys study and understand? If you don't understand, then if you don't understand this is the basic. Okay, this is the foundation. Okay, so you have to have good foundation to proceed later on when we go and solve a problem. Okay, and we say, oh yeah, this is why. Okay, because we took this class 261, and that's why. Any questions? All right. No questions? Okay. Let's stop recording. We stop recording.